Good morning, guys, and welcome back to the last part of Chapter 17, Kinetics of a Rigid Body in Rotation and in General Plane Motion. So far, we talked about the moment of inertia and how to compute it as the resistance of rotation. And we talked about the translation and the equations of motion in translation for a rigid body, and we said that in this case we have three equations: sum of x equal magx, sum of y is equal to magy, and the sum of moments around this center of mass is equal to 0 in translation because there is no rotation. Or we can take the sum of moment around a point A by computing the sum of moment of all the forces around this point A, or in other words, we know that the resultant force is equal to mag, so we can multiply mag by the distance from this resultant force to this point A. Now, in this video lecture, we're going to talk about kinetics of a rigid body, but in rotational motion. So what if I have a rotational motion? In fact, if I have a rotational motion, and I know that this is the center of mass G, I know that the sum of moments around this center of mass in rotation should be equal to I times alpha. What is I? I is the mass moment of inertia around this point. And if you remember in the first video lecture of this chapter, I did the analogy between translation and Newton's second law in translation and the sum of moments in rotation. And I said that the sum of forces should be equal to m times Ag. This is the second law of Newton in translational motion. And this is also similar to this equation. The sum of moments in rotational motion should be equal to I times alpha. Now, what is this term? It's the sum of all the moments exerted on this body with respect or about an axis that is perpendicular to this body passing through the center of mass G. What is I? I is the moment of inertia around G. Don't forget that this is around G because I'm searching now for the moments around G. Now, Ig could be computed depending on the shape, as we did in the first part of this chapter. And what is alpha? Alpha is the angular velocity here, which is equal to d omega over t, where omega is the angular velocity. Now, what you have to know is this Ig is similar to this m. I know that this m is the resistance to do any translational motion, which means this I is the resistance to do any rotational motion. So in fact, guys, if I have a rotational motion, I should use this equation or a similar equation that we're gonna talk about later on. And don't forget, guys, that if I have a rotation, then this point, the center of mass, will do also a curvilinear motion. So imagine, guys, that you have a rotation around this axis O, passing through O. Then this G will do a curvilinear motion, all right? This curvilinear motion means that I'm gonna have what? I'm gonna have a normal acceleration and a tangential acceleration. And don't forget that the tangential acceleration stands for the change of velocity, and it's always tangent to the curve, while the normal acceleration stands for the change in direction, and it's always towards the center of rotation. And what is the center of rotation? Here in this case, it's O. That's why AGN is directed towards O. And this means, guys, that I can have three equations, which means I can have three unknowns. These equations are sum of F normal direction is equal to M times, of course, AG in the normal direction, and sum of FT tangential force is equal to MAG T in tangential direction, and the sum of moment, of course, around the G will be equal to the most moment of inertia around the G times the angular acceleration. Now, remember, guys, that AGN is equal to omega squared RG. In a vector form, it's equal to omega squared RG vector with a minus sign, so it's equal to minus omega squared RG because it's opposite to the radius, and AGT is equal to alpha RG in a vector form. It's equal to, of course, alpha cross R, and now here in a scalar form it's equal to alpha times RG. So I can replace them here, and these are the three equations that I can use in order to find three unknowns only. Now, what if I want to find the sum of moment around an arbitrary point that is different than the center of mass? In fact, you have to know, guys, that if I want to find the moment around any point, I need to find the resultant force moment. So I know that this resultant force is located, let's say, at the center of mass, and I know the distance from this center of mass to this point, and I can find the resultant force moment. And the second term is the moment of inertia. Since I have a rotation, I'm going to have an inertia. And this inertia force will have a moment. This moment, in fact, is equal to Ig alpha. All right? So, guys, it's the same as the translational. There is a very strong analogy between the translational motion and the rotational motion. In fact, this term here, which is MAG, is called the force of inertia. It has a moment, and this moment is equal to Ig alpha. All right? So if I want to find the sum of moment around any point that is different than the center of mass, I have to find both terms. The first one is the moment of the resultant force located at the center of mass around this point, and the second one, I have to find the moment of inertia or the moment of this inertia force, which is equal to Ig alpha. And this means, guys, that if I want to find the sum of moment, let's say here around O, let's go back, this is O, O is the center of rotation, then I need to find the moment of the resultant force first. Now what is the resultant force? It's MA. And A has two components, AG and AN. However, here in this case, since O is the center of rotation, AG passes through O, so it doesn't have any moment around O. The only component of the resultant force that has a moment around O is AGT. Alright, so don't forget, guys, that the resultant force in vector form is equal to MAG, and this AG is equal to AT plus AN. Alright, so if I need to find the moment of the resultant force, I can find the moment of MAG because they are equal. Now, since the normal acceleration passes through point O, then this normal acceleration doesn't have, or MAGN doesn't have any moment around O. And the only force that has a moment around O is the component of this resultant force in tangential direction, which is equal to MAGT. Alright, so MAGT times the distance between G and O that I'm gonna call RG. Alright? And we said that it's also equal, it's also the sum with what? With the moment of the inertial force, which is equal to Ig alpha. Now, what is AGT? AGT is equal to alpha times RG, alright? So it's equal to alpha times RG. Now I can take alpha as the common factor, then alpha m RG squared plus IG. And remember, guys, what is IG plus m RG squared? It is, in fact, the moment of inertia around point O using the parallel axis theory. And from here, guys, comes this equation. The sum of moment around O is, in fact, equal to IO alpha. And don't forget that IO alpha is equal to IG plus mg RG squared. All right, so now I have three equations with the three unknowns, either to use sum of moments around the G or to use sum of moment around O. You have to identify which equation is the easiest one. All right, this depends on the given. All right, and this is the procedure for analysis. Of course, I have to establish my reference, my free body diagram, compute IG or IO, and write these three equations and find these three unknowns.